This is MNIST from scratch that I made just from logic and memory. It scored a 97.94% accuracy in about 2 minutes on an 8 gigabyte laptop. So I'll go through it really fast. There's importing the PyTorch modules and so on. And this is grabbing the data, which the training set is 60,000 images and the test set is 10,000 images. So this random, it picks random pictures, so it's not training in order. And this is setting up the data for the training. And this is the targets, like what the answers are. So this is, the images are 28 by 28. And so I'm doing 28 times 28. And that's 784. And it's converting each image into one really long picture, is one way to think about it. A long, thin picture that consists of 784 numbers. And it's picking random picture, converting it into float. And this is the weights creation. And if notice right here that the second dimension is the same as the first dimension on the next layer. Same pattern follows. Second dimension here, same as first on the next layer. Is because they have to link together. So this has to connect to this, and this has to connect to this, and so on. So, and this is for lowering the numbers so they don't get too big. This is making a torch tensor 0. This is setting the batch size, number of epochs, learning rate, and it's a kind of a scaled learning rate. So it adjusts the learning rate based on the number of epochs or whatever. Let's see, loop count for I in range this, blah, blah, blah. So this is the forward pass right here. And this is the X batch. This is normalizing the numbers so they don't get too big. This is the Y batch. This so it can batch process. It learns a bit different if it batch processes, and it helps with speed like a lot if you're using a graphics card. This is the X batch matrix multiplied with the weights from up here, and then that is placed in the ReLU, and the ReLU is just the maximum of 0 or whatever the input is. Basically, you picture a whole bunch of numbers, like list of numbers or vectors of numbers, and if any of them are negative, just turn them to 0, and that's what this does, the ReLU, Rectified Linear Unit Activation Function. So then the output of that is then matrix multiplied with W2. The shapes stay the same. All this is doing is turning any numbers to 0 that are negative. And so the shapes are the same. So the 512 connects to the next 512. So that's what that's doing. Or sorry, that's what this is doing. That's connecting to this. And that's also passing through ReLU. And then it does the last layer where it's adding a bias to that, and it outputs the logits, which are the raw predictions. Then this is the softmax, or it's converting to softmax, where it turns it into a probability distribution. And this is adjusting for, it's subtracting the maximum numbers and so on. So it's not too high for the exponential output, because you have E, which is about 2.71828, raised to the power of that. So normlogits.exp. So it's E about 2.71828 raised to the power of the logits. So come down here. This is counts sum, or it's the sum of the counts, which is the sum of all this. The reason for this is so that it can go on the bottom of the fraction. It can type it like this, because if you raise something to a negative power, that's the same thing as inverting it. and raising it to that power. Like, just say if the count sum, if it was just one number, like 3, it would be 3 raised to the negative 1, which means 1 over 3 raised to the 1 power. But when it's in this form, you can use the simplification of the power rule for the derivatives later. So come down here, this is the probabilities, which are the softmax outputs. Probs equals softmax equals this. So this is normalizing it, and it'll come out with a batch of list of numbers is one way to think of it. It's actually tensors, but each tensor is the neural network's prediction of the likelihood that the digit is a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Just say if it's 22% sure that the digit is a 9, then it might be, different amounts percent sure it's the other answers. But the total would sum to 1. So all the other 9 answers would be 78%, because the 22% plus the 78% equals 100%. So this is the loss calculation, where it calculates the loss with or right here, it's the batch loss. What it does is it takes the natural logarithm of the target class output. And just say if the answer, the answer is 9, then it'll only grab the index location 9, and it'll grab the index location 9 from the probabilities, and whatever value that is, it'll do that for each of the images in that batch. Then it'll take the average of that, and it will take the negative of that, and it'll output the loss value. And the loss can be used to see how far off the neural network is from the correct answer. Okay, then you have the backward pass. I'm not going to go in detail to this because it's a lot of detail. It'll take a long time. But this is the backward pass where you calculate the local derivatives and chain them together, which chain means multiply, but it takes getting the shapes correct, and that's one of the main complex parts of the derivatives calculation. So once you do all of that, then you end up with the derivative of the loss with respect to, or by infinitely small increase in, these 4 things: W1, W2, W3, and bias 3. So you can see how much each of these, the W1, W2, W3, and B3, how much each value affects the end result, and calculate the derivative and multiply the learning rate with that, and then subtract that value from the original weight, and that updates the weight. It updates the weight to the new weight. So here's the new weight: weight 1, weight 2, weight 3, and the bias 3 as well. Follows the same pattern. So once it does all that, it prints the loss from up here, it's called the categorical cross entropy loss, which it simplifies down to the negative natural log of the target class's probability output. And in this case, it's in a batch, which is typically in batches. So it's in a batch, so you take the mean, or the arithmetic mean, also known as the average, and then take the negative of that, and that gives the loss. So down here it prints the loss. So it'll go back up to this loop and iterate to the next batch, and it will process and train on that, update the weights based on that, and do it over and over until it runs out of batches, until it's processed to 60,000 images. And the number of epochs is how many times it goes through those 60,000 images. So it outputs the loss each time, and as you can see here, this is outputting the loss for each epoch, and it was this to begin with, then it got slightly better, or that looks the same because of rounding, and then that's slightly better. And if we go down here, this is where the test is. It's basically the same four-pass, except it's using test data that it hasn't seen before. And it's picking random images with the renperm, and then it's outputting, or it's checking the test images. It's inputting test images, and the neural network here, the forward pass, will check against the correct answers, and then it'll output a percentage, and it comes out to be 97.94% on here in about 2 minutes on an 8 gigabyte laptop that's about a decade old. So these are the settings that got that percentage. So that's an overview of how the forward pass works for MNIST from scratch, written from just logic and memory without looking anything up and without using AI. If you have any questions or comments, let me know, and thanks for watching. Please hit that subscribe button, and it helps me know if you want more videos like this. And thanks for watching, and please click like and subscribe. Bye.